Good evening and welcome everyone for this FriQuant Seminar here. Today it's Wednesday, even though we generally have it on Fridays. And we are very happy to have Dr. Syamsundar from IIT Kharagpur here to give us the seminar. And as you can see, it's about this year's Nobel Prize. And he's been fortunate enough to work closely with one of them, Alan Aspect, right? Yeah. So maybe let me give you a brief background of Dr. Syamsundar. So he had done his BTech in radio physics and electronics from Calcutta, and after that he obtained his master's in applied physics from École Polytechnique and Institute of Optics Graduate School, and he was under French government scholarship at that time. And in 2015, he completed his PhD from Paris Saclay University under Professor Fabian Bretenacker. After that, he had been a postdoc at two different places. First at Castle Brussels lab at Sorbonne University. Is that in Paris itself? Yeah. And also between 2018 and 2021 in Germany, Paderborn University. And since the end of 2021, he joined IIT Kharagpur as assistant professor in the Advanced Technology Development Center. So in fact, yesterday we did have quite some amount of discussions with him. So he does very interesting experiments on photonic quantum computing, quantum walks, and so on. So his area of research interest is experimental photonic quantum computing or quantum information processing, quantum optics, noise, laser dynamics, and so on. With this, let me request Syamsundar to give his talk.
Yeah, thank you. Thank you everybody for being in the seminar, and thank you for this nice introduction. First of all, I also thank I have Quantum Technology Foundation for giving me this platform. This is such a huge honor for me, and also because of the fact that this is on a topic which I guess is of everybody's inspiration and motivation to do on future works on this topic, right? Particularly being a student, being a researcher in this field. So, as it has been mentioned, that today's talk would be this year's Nobel Prize in Physics, and this was about entanglement, quantum entanglement. And in fact, from its very beginning of the story of entanglement, it has been puzzling to even the inventors. And in fact, it was one of the mystery as quoted by Richard Feynman. So the journey started from being a mystery to nowadays we are exploiting this mystery to develop potential technologies, being it computation, being it communication, be it simulation or even sensitive measurements. So you see the entanglement kind of completed a journey starting from a puzzle to the community, which was in fact kind of questioning the validity of the quantum theory itself, from a tool. Now we are hoping to use it for technology development. So and for this journey, this year's Nobel laureate, they were instrumental to complete this journey. And today my plan is to revisit this journey along with you, of course, and in the meantime, hopefully we would learn at the end about this year's Nobel Prize in Physics, right? So without much ado, first of all, let's all together congratulate this year's laureates, Alain Aspect, John Clauser, and Anton Zeilinger. So Alain Aspect was he's from France, he's from United States, and he's from Austria, okay? And I have been fortunate enough, in fact, to be a student of Alain Aspect when I was doing my master's in École Polytechnique. So he was in fact like my teacher for the quantum optics course. and he was teaching that with Fabian Breitenecker, who later on was my supervisor for doing my PhD. And also Alain Aspect and Fabian Breitenecker being close associates, I have been kind of opportunities to have both scientific, non-scientific chats with Alain Aspect for several occasions, and I can assure you that of course he's one of the brightest mind, but he is also deeply kind of knowledgeable to other cultures, other countries, their socio-economic conditions, and so on. So just give me this opportunity to tell you a story. Huh? So so it was in my first or second class or something during my master, and so there were. This was kind of one of the first course which was given in English in the history of École Polytechnique, because it was French institute run by military, still now run by military, introduced by Napoleon and so on. So this was the first one. We were one of the first students of the batch, which the course fully was developed in English, and so there were few Indian students, and 4 of them were Bengalis. And Alain Aspect knew that Bengali guys are very fond of fish, and if it is Ilsa, then there is okay, it's icing on the cake. So he was saying, you guys are Bengali, right? So you like Ilsa, and you must be starving for it here. And so there is a place in France which is Bordeaux. So those of you know it's very famous for French wines and so. But he was saying, mind it, you can have very good fish over there. So you see, so being such a very famous person and so on, he had such very detailed knowledge of different cultures and such a diverse cultures in India, and still knows about even Bengali culture. Let's pick it that way. Of course, we had occasions. He was discussing about Satyam Bose, C.V. Raman, and so on. And also, there were occasions when he was asking, okay, how is your PhD going? And okay, yeah, I said, okay, ask my supervisor. But you shouldn't do that, because the students, you shouldn't do that, because the work he did, for he's getting Nobel Prize. It is his work what he did during his PhD. So of course then he must be thinking, what a stupid guy, he doesn't even know what he's doing on during his PhD. Anyhow, of course I had also some occasion, a couple of occasions to not really meeting but seeing Anton Zeilinger in some conferences, but still no opportunity to see closer, but hopefully maybe in one day. Anyhow, so if I may quote, this year's Nobel Prize is for experiments with entangled photons, establishing the violation of Bell inequalities, and pioneering quantum information science. Okay, so let's have a look of what this entanglement is and why this is so important, and how people or the Nobel Committee thought that this work is something which is worthy of the prize. And just to tell you the importance of this quantum entanglement, I would quote simply Schrödinger. So he mentioned here that I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So before entanglement, people thought that, okay, quantum superposition is only the one mystery, which is, or the basic characteristic trait. But after, as soon as the concept of this entanglement thing came, as we are going to see in few slides, then Schrödinger, being one of the founder of quantum mechanics, he realized its importance, and just immediately after he said this, and also this entanglement name was introduced by him as well. Okay, so you understand this was very, very important to the founder as well. So maybe just to better understand what quantum entanglement is, we can think of first like quantum superposition, right? So in quantum superposition, technically speaking, it says that a quantum system can be in superposition of all possible states. Okay. So for instance, in this cartoon picture, let's see if this ball is a quantum ball, then it can be in both like white and black at the same time. Okay. So now, what is quantum entanglement? So in this similar analogy, quantum entanglement tells us that there can be some sort of correlation when we talk about two physical quantum systems, which sets, for instance, if we see this ball to be again like white, the other ball would have a black color. Okay, so of course you can think, okay, what is so special about this like this kind of correlations? To emphasize on that point, we can think of some sort of this kind of experiment. So here you can think of, I have a source from where, like, two balls are thrown in two opposite directions, and for instance here, like one observer, when he finds the ball and sees it, when he finds it white, of course then he knows the other one would have the black ball, because the source is throwing in each term like one white, one black ball, right? So there is, okay, what is the mystery here? But in the quantum case, the mystery is here that it says that the observer does not know the color until it sees the ball. Okay, so in other words, that if the balls are quantum, before seeing it, the balls were actually gray, no color. Okay, so as soon as, for instance, one observer finds the ball and sees it white, the other one immediately turns out to be black, and in vice versa. Okay, so this was really puzzling for the inventors of quantum, again, quantum entanglement, and this is the topic we are gonna explore today. Okay, good. So how this thing came? So first thing, the first idea about quantum entanglement came through this paper by Einstein, Podolsky, and Rosen, through this paper which would later on be known as this famous EPR, named after these three guys, like EPR paradox. Okay, but what is so paradoxical, if I may put it that way, about this thing? Okay, so in the previous example, as I described, right, that okay, the ball was gray, but once I see it, I like immediately the color turns out to be white, or in the sense, if I see it white, then the other one turns out to be black. Right? So this was the thing, was very puzzling to Einstein. Why? Because, and also along this line, Einstein once commented that, do you think that if I'm not looking at the moon is not there? Because so in Einstein, the concept was that the physical reality, the result of, or like properties of a system, let's pick it that way, it should be independent of measurement. Okay, so as I said again, that if it's independent, if I'm seeing at the moon or not, the moon is still there. So along that line, so that was very puzzling for Einstein. He was saying, okay, so I can use this because this quantum entanglement was allowed by the theory of quantum mechanics. So he was thinking that, okay, so now I can use quantum entanglement to actually kind of invalidate the quantum mechanics theory. Okay, although he was like one of the very pioneer of this theory, but he was never really satisfied, particularly with the interpretation of quantum mechanics. So like he found, okay, I can use quantum mechanics in like kind of implication to use it against its validity. So immediately after that, this paper, of course, again, another like founder of quantum mechanics, Niels Bohr, who was of course like very kind of in favor of quantum mechanics, like he immediately refuted, saying that no, when we are talking about quantum entanglement, we cannot talk about individual system. We need to look at like the whole system as a whole. And this debate between like, if quantum theory is complete or it needs to be like, compensated with a bigger theory or broader theory, so to speak, was going among these two, or mostly these two, like Einstein and Bohr, like for decades. And to be honest, the community itself was not paying a lot of attention to this debate. One reason may be the fact that by then quantum mechanics was having great success, in a sense, for a lot of microscopic, particularly for microscopic observations. There was no like proof itself that quantum mechanics is not true. On the other hand, like this was more like a kind of matter of taste, as you would see later on. Like Einstein said, okay, this is I do not like the interpretation, but I'm not saying the quantum theory itself is invalid. So in his mind, he has the idea that, okay, quantum theories should be something, or maybe like it's a very, how should I say, it's a limited version of a bigger theory. Okay, so so the community was thinking, okay, these are the two big shots. They're like, okay, having some philosophical debates among themselves. We forget, we just use quantum mechanics and carry on. Okay. Anyhow, but the situation changed like almost after 30 years when John Bell kind of took this debate seriously and did mathematically show like a kind of a bound where, for instance, the Einstein's model of physical reality would like fall in, whereas, for instance, this bound in certain cases can be overcome using like quantum physics. So you see, so this philosophical debate about this topic kind of moved from a philosophical debate to a question of like experimental validation. Okay, so and that's where the contribution from like our Nobel Laureates started to flow in, because they took this Bell's which later would be known as Bell's inequality. They took this inequality and put it into an experimental test, which later on like validated, so to speak, like quantum theory, and not only validation of that, but rather used it for the technology development. Okay, okay, good. Now, so to better understand again this Einstein EPR, or Einstein-Podolsky-Rosen paradox, and it's like Bell's inequality, and again like the experimental implementations of that, so on. So let's do what Einstein said, like a Gedanken, or thought experiment. Okay, and so this is not exactly in the form what was proposed in EPR paper itself, but this is more kind of a modern form of that, which is close to, in fact, the experimental implementation of that experiment what done by this by the Laureates itself. Okay, so so that's why I guess it would be better that if we start in this formalism itself. So suppose that we have a source which emits like two photons in two directions. So the two photons here, for instance, I labeled it as like one in red color, other one is blue color. So you can think of like of two different frequencies, and you can have frequency filters to see them and so on. So the point here, what I want to insist here, that for this purpose, we don't need the indistinguishability of the photons. They can be distinguishable, which of course later on I would not speak too much about it. So this feature is not related to indistinguishability. Okay, okay, good. And on these two photons, we do polarization measurement. Okay, so using, for instance, a polarizer. So people who are not familiar with polarization measurement, if you are more familiar with spin measurement, you can think of like, okay, here like same experiment in with spin half particle, spin up going in one direction, spin down in the other direction, and here you do kind of a spin analyzer like a Stern-Gerlach kind of experiment. Okay, so one spin, the up spin goes up and down spin goes in other port and so on. Okay, so here for instance polarizer, nowadays people use polarizing beam splitter, like of course then it was not available, but anyhow, so what it means that okay, if the polarization of the incoming light is along the transmission axis of this polarizer, then it goes in the along one port. If it's orthogonal to that, then it goes in the other port. Okay, so if this one is +1 for instance, this one is -1. So we do similar kind of measurement also on the other photon using another polarizer. Okay, and for instance this angle is this like let's say axis of transmission for this polarizer, and this angle B is axis of transmission for the other polarizer. Okay, so now of course we have like many possibilities for the detection. One is this single detection. Okay, so single detection means okay, I have like detected one photon in this channel, which is this P plus in the photon detected in the plus channel when the polarizer is oriented along A. Okay, similarly photon detected in the minus channel, polarizer is oriented along A, and same for this measurement on the B photon, right? So mind it here, this picture is already quantum, because you can think, right, it's not classical that in the if you have a classical beam of light, you put a polarizer, then okay, factor of light goes in one port, the factor of light goes in the other port depending on the polarization orientation of the axis. So but here when we are talking about single photon, the single photon can only go either to there or there, so you cannot divide it, right? You cannot, so meaning it's already quantized. Okay, so and that's why we are talking about here probabilities of detection. So intrinsic, so this statistical or probabilistic interpretation is intrinsic to this quantum feature already. And of course now we have, I mean the situation would be much more interesting, as you would see when we look at like joint detection. So what it means that okay, again that probability of detecting one photon in the plus channel, similarly jointly detecting the other photon in the plus channel when this polarizer is aligned along A, this polarizer is aligned along B, and so as the other terms. Okay, good. Now with this measurement setting, now suppose we have an entangled state or EPR state of this form. So people here who are not very familiar with, let's say, quantum mechanical formalism or quantum mechanics, so to speak, let's I mean don't worry, we would try to discuss, make it like as understandable as possible. So take the first term. So here it says that this red photon is polarized along X in this reference, and the blue photon is polarized along X. Okay, so the two photons, so this term says that my red photon polarized X, blue photon polarized X. Good. And this term is saying other way, that my red photon is polarized along Y, my blue photon is polarized along Y as well. Okay, and Z is propagation direction, orthogonal to that. Okay, good. So, however, quantum mechanics allows you to have superposition of these possibilities. So, what does it mean? So, it means that the two photons can have polarization that and that. Okay, mind it. So in classical optical analogy, you might think that means the two photons have polarization along certain angle between these two directions, but that's not the case. It's really this and that. Okay, it's not in between. Okay, so this is, you see, right, this is very counterintuitive to our, let's say, the usual sense of our understanding, which would later on like bit clear. That's what we want to clarify, and this was also very misleading for Einstein as well. So don't worry, this should be misleading for us. Anyway, what is quantum mechanics prediction? So quantum mechanics predictions, I mean if we do a little bit of calculations again using quantum mechanical theories, which is very standard and not very difficult as well. By the way, all these calculations and like kind of the logical statement I'm saying, you can find it in the book written by Alain Aspect itself. And so there is a particular chapter where it was discussed like along the line I'm presenting today, and that's the line of, that's a logical thing I have been taught. So of course I couldn't escape that. Anyway, so you see, so these are the single probabilities what we have. Single probabilities is like half, meaning you have equal probabilities the photon to be detected either here or there. So that means like for single detection perspective, the polarization of the photon is completely random. Similar for the other one as well. However, now again, if we do look at joint detection probabilities, so that's the form we have. You see, like, of course, being this cosine square or sine square, we expect some kind of correlations that depends on the angle between these two axes. Okay, good. Now, so to better understand the correlation itself, like it is kind of a standard way of looking at such kind of a correlation coefficient, which is this E here, and as you see, it's kind of addition of the similar terms, meaning either both photon there or there, to like when one photon there, other photon there, or vice versa. So the similar term minus the opposite terms. So now, if we look at, for instance, when these two polarizer is aligned, meaning their angle between them is 0, then what we get, that the joint detection probabilities is exactly half. So you might think, okay, why I called previously to be correlated, but if you look at the single detection probabilities, this is also half. So that means the conditional probabilities is 1, or so that means total correlation. If you're not like seeing it, so look at the opposite terms. So this says that if I detect a photon which is like in the plus channel, then no way I can see the other photon to be in the minus channel. Okay, so this is total correlation, and this is the quantum mechanics prediction. And of course, in general, so this is a special case when the angle between the polarizers are like like 0, but in the general case, this takes this form. Okay, so quantum mechanics can give you total correlation. So that was the type of correlation like I was talking when I was introducing this entanglement. Okay, so now so that's kind of the kind of standard method of doing the quantum mechanics calculation. So now we would again do the calculation like on board, and in a bit like, let's say, non-standard way. But this, in my opinion, I mean, in as I was saying, like as introduced in the book, this gives you maybe a better clarification of the type of logical statement what like EPR paradox was saying. But of course, I mean, it's two different type of calculations, but definitely it would give same type of results. Good. So in this, let's say, type of calculation, we would be saying that this photon maybe comes to the measurement set a bit early, so we could do the measurement bit before than the other one. Okay, so that's what it is saying, that we are implementing measurement on this photon. Okay, so as we saw before, that we can have measurement result +1 or -1. And quantum mechanical formalism says that if we do a measurement, the quantum state or the wave function collapses to the eigenfunction of the observable we are looking at. Okay, so that means if we do detect the photon here on the plus channel, so that means the corresponding state after the measurement is x, and from here for the entangled state, that means the wave function after the measurement is xx. Similarly, if we do the measurement on, like if we find the photon in minus channel, so that means the wave function would collapse into yy. Okay, so now you see, if we do the measurement like in this polarizer, I mean using this polarizer, then of course once we get like +1 result in this measurement, since the state is collapsing in this state, so the other photon, the second term here, should be in the plus channel, and similar for the other one. And in general case, this should be following this cosine square law, which is this Malus law, as I said in the previous slide. And this is, kind of very like it was completely unacceptable to Einstein, because you see here it says that if I do a measurement here, it instantaneously changes the state of the system such that the measurement outcome of this measurement would be determined beforehand. So it's kind of indicating towards kind of superluminal propagation of information, and Einstein being the pioneer of relativistic theory, that no signal or no information can propagate faster than light, it was completely unacceptable to him. So he thought, okay, I can use this to really question about the validity of quantum mechanics, because this is kind of, in his opinion, was like kind of as we saw that kind of questioning either validity of relativity, which was not, in his opinion, of course not, but otherwise it is like questioning the validity of quantum mechanics. And of course he was on the first kind. And that's the type of argument based on this kind of physical questioning he put on the floor in this paper, that the quantum mechanical description of reality given by the wave function is not complete. And or when the operators corresponding to two physical quantities do not commute, the quantities cannot have simultaneous reality. Okay. So you see, Einstein was of course like very philosophical in this sense, or like, how should I say, like, or politically correct, that okay, he was mentioning about the validity of the quantum mechanics theory as well, but he is also finding another path, that if this statement is not true, then this thing we should accept and move on. And of course Niels Bohr was falling in this second category, because he was true believer of quantum mechanics and quantum theory and so on. Okay, but again, mind it, Einstein was not questioning really to the how should I say, like the kind of quantum mechanical theory formalism, but rather its interpretation. And it would be clear maybe through this statement, as he was saying, that indeed one would not arrive at our conclusion if one insisted that two or more physical quantities can be regarded as simultaneous elements of reality only when they can be simultaneously measured or predicted. Okay, so in fact, like as I was saying, Einstein was from the very beginning of quantum theory, he was not very satisfied with the statistical nature, the intrinsic statistical or probabilistic nature of quantum theory. So in his opinion, the theories should not be statistical. So you may counter, okay, why there is this statistical physical theory. So for that you might think of, for instance, right, like Maxwell-Boltzmann distribution. So like it gives you a velocity distribution of molecules, let's say, flying in this room, but in the hindsight you can think of also like an individual molecule, then you would have trajectories, and then you can write like equations for each molecule, and then you could do it. Of course, it's super complicated. Statistical mechanics gives you a more convenient way of describing what you want to see at the end of the day. But of course, like this, like trajectory of individual molecule, I mean, that's not excluded, right? And Einstein had in his mind this kind of thing, that okay, that there must be a broader theory which can, like in a limited case, can explain the statistical predictions of quantum mechanics. Okay, and this was the scenario, like until, again, as I said, after like 30 years after their first, like this EPR paradox was introduced. And the situation changed, as I mentioned before, when John Bell like took this debate and put it on to experimental experimentally measured quantities or bounds, so to speak. So this is this famous, which is known as this Bell inequality. So what is that? So so Bell said, okay, good. So as Einstein was saying that, okay, the physical reality should be independent of doing measurement or not, meaning that there should be some hidden variables to the photon which would like kind of determining the result of the measurement, which we don't know. No theory present that time knows, but we can define it. So let's say that's the parameter. It can be anything, any parameter. There is no restriction on this, like which, following the EPR analogy, this hidden variable. And yes, lambda is a common property which is determined by the source. And then, so that this lambda can change, for instance, like pair by pair, one pair, one lambda, next pair, and the lambda, and so on, which is the reason, for instance, having this random measurement outcome, because we are having random outcomes in the measurement, right? So meaning, okay, it's a probability density with of course satisfying this condition being a probability density, and you see there is no particular form of lambda which is defined here. And we have measurement results, right? So we have, as we saw, that okay, it would be +1 or -1. Now if you look at here, that the measurement result depends on lambda, so which is like this hidden variable, and the measurement only like on one of the photon. So here you see, like it's not A and B, it's only A, meaning local measurement only one photon, right? Or one of the system. So this is this localistic view that okay, I'm not considering that one measurement would affect my other measurement and so on. So that's why this localistic and realism, in a sense that okay, I'm saying that my measurement outcome is dependent on some variable. It doesn't change because of the measurement. Okay, good. And then the correlation coefficient, as we introduced before, it depends on, of course, as you know, like two measured quantities and this probability distribution integrated over all possible hidden variables. Now we introduce another quantity, let's say this S, which again some weird combination. In the first glance you might see weird combination of these correlation coefficients. But if we look at, for instance, in this one and do a bit of like rearrangement, we find this form. Okay, so now it's very easy to check that this should be -2, right? Because we as we saw in the previous case, that B lambda B or A lambda B should be +1 or -1. So in any case, that if it's, for instance, +1, then this term would be 0, and then these two terms can be what? So this one can be +1, this one can be only +2. In other case, this one in the negative sense, this can only be -2, and so on. So this is what we have. Now if we do, let's say, repeated measurement, measurement on repeated pairs, so of course that means that we are doing like kind of averaging over all possible lambdas. So then that's what the bound we get. So this is this famous Bell inequality, which is in a bit modified form by this Clauser, Horner, Simony, and Holt, or CHSH Bell inequality. This the Clauser is the Clauser who got the Nobel Prize as well. And where this as you see here, this depends on the correlation and only on measurement outcome. Okay, so this is the bound where any local realistic model would fall in. Now see what quantum mechanics tells us. Good. So as we saw in the first case, that this is our bound, but here just be mindful here that we are talking about measurements for two different settings of the polarizers. That this one can be A prime, and this one BB prime. Okay, this is the bound. Now, as we saw in the previously when we were looking at the quantum mechanics calculation, that this correlation coefficient would be cosine like twice the angle between these two polarizers. Now, take the simplest case or also the very important case where all these angles are pi over 8. Okay, so meaning, so this one, then 1 over root 2, 1 over root 2, 1 over root 2, and this one 3 pi over 8, so minus 1 over root 2 with minus another 1 over root 2, right? So meaning this is 2 root 2. Of course, as you see here, this is violation of the Bell inequality. So you see that okay, quantum mechanics clearly violates any like local realistic hidden variable theory. So now it's not anymore a matter of taste, interpretation of quantum mechanics, but rather, okay, just go to the lab and test, and then let's see if we can, if we like, who wins. Is it like this hidden variable model or quantum mechanics? So this is where like the contributions from the Nobel Laureates started to come in. In fact, like, you know, not many people, to be honest, even after, like, you know, Bell's theory, Bell's inequality came up, got interested into that. But anyhow, as you already saw, Clauser was already interested. So he again like put the Bell's inequality in a form which was more like realizable at that point, like experimentally. So that was his first contribution. But during his PhD, he was like actually a kind of molecular astrophysicist or something like that. But of course, having strong interest in foundations of quantum mechanics, so he was doing in the University of Columbia, I believe, where he was doing his PhD. But in the meantime, like he realized that there is one experiment in Berkeley who produced like entangled photons. So then he was planning that he should go there, but he couldn't join the same group, but he joined the group of Charles Townes. You know, of course, like who's famous for I mean, one of the founding father for lasers and things. And Charles Townes hired him for doing interstellar molecular spectroscopy, finding like molecules in the interstellar like regime, and because he was also pioneer of that field. But Clauser's interest was also aligned to do kind of this test of Bell inequality. So and it was with Professor Cummins and the PhD student who developed this like, you know, source of entangled photon. I mean, by then he left. So Clauser and then the PhD student, this Friedman, they kind of convinced the supervisor that no, we should work together, and we have blah blah blah, we can do amazing things and so on. So Clauser being a postdoc and Friedman being a PhD student, they like did the first experimental demonstration of Bell's inequality. Okay, so this was the kind of experiment, and the entangled photon was created through, like, you know, through this calcium atom. So excitation, which is not direct but indirect excitation of this 6,1s0 rebel, then the 2 photon is emitted because of the spin conservation. You get like entangled photon. However, like since this was like indirect excitation, and as you see here, it is with like hydrogen, I mean deuterium arc lamp. So of course, like, you know, it was not perfect and so on. But anyhow, so this is the coincidence rate, what quantum mechanical prediction shows, and this is like, you see, like they could very well like demonstrate what is expected. I mean, what is kind of given for quantum mechanical theory. And more particularly, so they reformulated this inequality. And in the classical case, this inequality should be less than 0. And as you saw here, this parameter is clearly violating this inequality with by then like 6 standard deviation. And they claimed like, okay, so quantum mechanics prevails. Good. However, like again, after that, Clauser didn't continue, but of course, it catch the attention of another laureate, which is who is Alain Aspect. And although the first paper came in 81, but he was interested in this topic starting from 75, but also like between these years, like like the laser technology developed like significantly, and he could benefit from that. So as you see here in the previous case, like excitation was through this hydrogen lamp, but here he could use like 2 lasers through 2 photon absorptions, like he could excite this high level, and of course the efficiency of the source by that way like increased tremendously. And so that's why they could reduce the measurement time, which was like previously along days, to only a few minutes. And so this was his like first let's say contribution to the topic, but he did like a series of experiment on that. And in the next one, for instance, in the previous case, as you saw, like it was only like measurement with like 1 channel of the polarizer. Which one? This one, yes. Yes, normalized, yes, the total count. So this is just like kind of normalized coefficients. That's what it means. So you don't need to do any normalization. It's already normalized. It counts. Sorry? Why? Why? Yes. No, it's not 1. It's total counts, right? It's total counts. It's whatever. No, I mean total counts. I mean you are doing measurement over a certain time, so you are detecting thousands of photons. Yes. Now it's joint detection. As you see, it's the total joint detection minus the correlation normalized to total detection. As we define in like any correlation, right? Is the like is the okay? Let me think. Yes, is the average of the product minus the product of the average, right? And normalize. So that's it. That's it is. So good. But thanks for asking. Good. So this is again the improvement in this case is from you see single channel polarizer to this like dual channel polarizer. So meaning you have direct access to this term. Where for instance in the previous case, like it was single channel polarizer, and this coefficient, R0 was when you don't have polarizer, meaning to have the same quantity you need to measure it with the polarizer, you measure the quantity without the polarizer, you normalize, and of course it's different experimental settings and so on, and it's like it's more complicated, also like prone to experimental errors, but here you get this quantity like directly. So this was this second generation of experiment, which because of this like improvements, it could show like the violation of Bell inequality up to like 40 standard deviation, as opposed to, for instance, 6 standard deviation as we mentioned like in the first example. But the third generation of experiment, I believe, which got the maximum of attention was this. So here, like which so to speak, like which closed this locality loophole. So what is that? So as I was saying, like that this Bell's inequality was based on one of the principle is the localism, that one measurement here cannot influence the measurement on the other side. Right? And Bell proposed that if we can do, for instance, like change the measurement settings between these 2 measurements, like less than the flight time of the photon, like to go here and there. So that means like our measurement is completely independent of the photons, like which is originated from the source, because it's 2 photons completely seeing random measurement settings, and so of course that means like locality should be like maintained in that way, and in this experiment they could like do this like verification. Particularly they used 2 switches which kind of directed the light polarizations, two different polarizations in two directions, and then doing similar kind of measurement as we saw on the previous case. So, and this switch was based on this more like acoustic effect and acoustic effect of using water. So it was really really funny because so since it was like atomic the photons emitted from atoms, so it was like kind of distributed over like wide solid angle. So of course all the optics for collecting as many photons as possible, it was really like big optics. And so like no provider can build a switch or polarizer which can dynamically switch the channels and to I mean that fast. Here this experiment, the two measurement settings was around like 6 meters separated, so which meaning like you need to do this switching which is only of the order of 10 nanosecond or 20 nanosecond. So this was the speed of switch we are talking about. So they could indeed again like validate this locality condition, or in other words closing this locality loophole and still validate the predictions of quantum mechanics. So with this allows me move to do like another kind of experiment, and again like after almost a decade or so, then like the third laureate, like he picked up this topic again, and by then there is like much more efficient source nowadays which is regularly used for entangled photon source is created. Nowadays is mostly based on nonlinear medium, and one of the, or particularly parametric down conversion. And for such kind of a process, you will need to have so-called this phase matching condition, or like two photons are emitted in a very like in a particular direction. So of course that means they could like couple these two photons like in fibers, and could take them like really long distance, and they could do this locality testing, which was in the first generation of experiment of like 400 meter away. Okay, and also on top of that, what they did like kind of true kind of truly random measurement setting. So meaning two random number generator for the two polarizer, which is like randomly changing the orientation of the two polarizer. So, and again they of course validated the predictions of quantum mechanics. So in a nutshell, this is the kind of the timeline how it propagated. So starting from the first generation of like Bell inequality violation with a single channel, to like again Bell inequality violation with better perfection, like closing the locality loophole, but kind of not so strictly manner, and eventually with very strictly manner closing the locality loophole. So that's how like was the status. But later on, like in all these previous ones, there is another like loophole, so to speak, which is called this detection loophole, in a sense, meaning that the detectors are not 100% perfect. That means it is only sampling part of the photons which are incoming. So nature might be cruel, and that there is someone can use this information. So like so to speak, this was under this fair sampling, that the detector, when it's taking some photons, is completely randomly choosing from the incoming photons. So this fair sampling like detector assumption was there. So the locality loophole in a sense saying that okay, suppose I have two measurements and the locality condition says that the measurement here cannot influence my measurement there. Okay, so of course then one easiest way to like satisfy this locality condition would be like to take the measurement settings far apart, such that like to have any kind of communication we need to propagate faster than light. Okay, that's the kind of argument, logical like direction was put by Bell. So that means now you can imagine, like if we can change the measurement setting, like which is less than the flight time of the 2 photons, so that means it's truly random for the 2 photons, right? So that was this locality condition, which was of course one of the condition needs to be satisfied to be inside this the bound, the local hidden variable theory bound, and this locality condition was maintained in the experiment, but still we could violate the Bell's inequality. Okay, so that was the essence of this locality thing.
Excuse me. Excuse me.
Yes, please.
Yes. So the lambda, the hidden variable, what we considered. Why did we consider it to be constant over space and time?
Constant over space and time. No, it's not constant over space or time, right? We are saying like it's changing because it's local parameter in us, because it's associated to individual photons, right? And we are saying it's right. So you have one pair of photon which is going to the 2 measurement, then next pair comes, and we are saying that in the next pair the random is different. That's why we are averaging at the end. So it's changing from pair to pair, because that's what your measurement is upon the photons, right? So of course it's associated to the photons. That's what we are considering.
But I am saying the random variable associated to a given photon, why should it remain same throughout, like?
No, it's not time. Same. It's changing photon to photon.
No, for a single photon. For a
yes.
single photon, why is it like? Why are we defining a single hidden variable for a given photon?
Yes, you can do many variables, but as I was saying, like there is no condition on lambda, right? It can be a set of variables as well. It's not like there is no restriction on lambda, because our measurement outcome is fixed. We have +1 or -1 for this. So that's it. And in the lambda, I didn't say anything about it. I just said, okay, it needs to be random, like in a sense that photon to photon is changing, and that, okay, effect should be measurable, as Einstein was saying, that it should lead to some measurable effect. So that means we defined a probability density for it, so that it's greater than 0, and since it's probability density, integration of all lambdas should give you 1. So that's the only condition we took. It can be set of variables as well.
So now that we know that Bell's inequalities are violated under experiments, so like what are the greater implications to quantum theory? Is it non-local, or like what is the implication basically?
What is the implication of Bell's inequality violation?
Yeah.
So fundamentally speaking, so Bell's inequality violation says that, okay, as Bell was saying, that like any effort to find for, like any hidden variable theory is doomed to fail. So meaning, okay, we should stop looking for bigger theory which can explain quantum theory, one fundamental thing, and application wise, many, as I'm supposed to say, let's say, if this audio problem is solved. The applications of this Bell's inequality violation itself. The complete description, in a sense that, again, no, like it's a test of validity of quantum theory from entanglement perspective, yes, or validity of quantum entanglement. It's a physical reality. Nature works this way, and we have to accept and move forward. By the way, so like to your previous question, so there is a very nice calculation on the book I was mentioning, the book of Alain Aspect. So if you're interested, also like, how, for instance, for different variables or different form of lambda it changes, so can have a look, or of course we can discuss afterwards as well. Anyhow, so as I was saying, like there is this detection loophole, and like, in between 15 to 17, there were like 4 papers which came like with same like goal, again, like including one of the laureate, like which closed both loopholes simultaneously, both the detection and locality loopholes. So indeed, quantum mechanics prevails. And moreover, like again, like one of the Nobel laureate, like Zeilinger, so they introduced like this another state which is like entangled not only among 2 parties but 3 parties. So to speak, this GHZ or Greenberger, Horn, and like Zeilinger state, and that this like viality of locality condition is still like valid, and in fact for this higher dimensional scenario, like you even don't need to invoke this inequality relation. And if you are interested, definitely you can see this article as well. But anyhow, so at the end of the day, quantum mechanics prevails, and particularly based on this thing that okay, quantum entanglement is true, and we need to accept. So like the Laureates, they have accepted it, but not only accepted it, but they used it as a resource. So resource for what we call nowadays, for instance, quantum communication. One of the thing is that which is this quantum teleportation, meaning sending quantum information from, let's say, one party to the another. And again, as a resource, you see here this EPR pair or entangled photon is used. So this theory came in 1993 and experimentally validated for the first time, like by Anton Zeilinger. Similarly, again, another application of application of interest is for communication is so-called entanglement swapping. As you can see here, for instance, if you have two EPR sources, then kind of doing a Bell measurement on one of the photon from each pair kind of swaps the entanglement between from 1 to 2, 3 to 4 to 1 to 4. And again, this entanglement swapping has implications. For instance, if we try to build a quantum communication network where, for instance, amplification of quantum signal is forbidden because of no cloning theorem and so on, and so you need some kind of repeater. For instance, for that, such kind of swapping technique can be used. And also there is this why this top part is coming. This part is bit anyway. So this is a bit annoying, the top one, because you don't see the title of the slide. Anyhow, so the other one is this so-called quantum key distribution. You can think of if the two parties are sharing an entangled state. So because of this perfect correlation or anti-correlation, they can use this for generating kind of perfectly correlated keys. And for instance, if there is some eavesdropper named Eve, if she tries to look into this channel, so one possible options for her could be that, okay, I use one part of the photon and re-emit another photon to this guy, right? The intended receiver. However, since she measured it and sending another one, so that photon would be not entangled with the Alice's part. So of course, if someone does then again Bell inequality test, that is supposed to bounded by the classical theory, not going to violate the Bell's inequality, right? So meaning it is intrinsically secure because of entanglement. So this is the protocol which was introduced by Eckert in 91, popularly known as E91 protocol, and again experimentally validated over in fact 2 islands by Zeilinger. Okay, good. So I mean, entanglement can be as a resource, not only, as I said, for different applications of quantum communication, but also, for instance, metrology. So there are so-called this noon state, so it is again another entangled state, so multi-photon entangled state, which is, for instance, is very useful for doing sensitive interferometry. Of course, for quantum simulation or computation, you need combinations of qubits and their interactions. So that means at the end of the day, you need entanglement over a very large scale. So this is what we nowadays called second quantum revolution. So definitely entanglement is really key for this second quantum revolution. So I would simply conclude by quoting the announcement of the Nobel Committee that this year's Nobel Prize is for experimental work. So in fact, for few previous years, particularly when I was in France between 2010 to almost 20 or 18, like, every year we were like, people were guessing that, okay, Alasp is going to get the Nobel Prize. And when he was not getting the Nobel Prize, people are saying, okay, because John Bell died, so of course you cannot give the prize to a dead, Nobel Prize to a dead person, so because of that, he is not getting the Nobel Prize. So maybe like because of this revival or really practical implications of the like, quantum entanglement, that this is not only fundamental, it is also had some implications, and because of that, like, they could give him finally the Nobel Prize. And also, if you read this statement properly, this would validate, I believe, like what I was trying to say, that the early Bell experiment drove the development, what is often referred to as the second quantum revolution. Two of this year's laureates, John Clauser and Alain Aspect, are honored for work that initiated a new era, opening the eyes of the physics community to the importance of entanglement and providing techniques for creating, processing, and measuring like Bell pairs in ever more complex and mind-boggling scenarios. And the experimental work of the third laureate, Anton Zeilinger, stands out for its innovative use of entanglement and Bell pairs, both in curiosity-driven fundamental research and in applications such as quantum cryptography. So you might be wondering why I dared even to speak in this, the work of the Nobel laureate. So if you are interested, like my research interest is also along this line. So in all verticals of nowadays, the second quantum revolution, starting from communication, metrology, simulation, and computation as well. So for instance, in the simulation scenario, we are looking at like high dimensional entanglement, or in other words, like, kind of entanglement between qubits, where we define like entanglement between two-level quantum systems or qubits, and this has potential, for instance, for like even higher security for quantum communication and so on, and also for computation as well. Anyhow, and also metrology, particularly again like exploiting spatial features of quantum measurement, and we were looking at particularly for resolving very short pulses better than what is, for instance, permissible by classical techniques, which defines, for instance, in the spatial case, so-called this Rayleigh limit. So using spatial properties of quantum mechanics or quantum measurement, so to speak, we could do a measurement with resolution higher than what is permitted by Rayleigh's limit. So, and in the domain of quantum simulation and computation, we are again looking at photons, many photons in a network of interferometers, and doing, for instance, simulation. So here it was more like simulating different level of disorders and dissipations, and also decoherence, so to speak, and how it changes, for instance, like the propagation of a quantum object in a network. In that sense, you can, by that way, you can look for like quantum transport phenomena in a very controlled way. And here we demonstrated that with controlled disorder and everything, like we can do transition from subdiffusive to diffusive to Anderson localization and so on. Okay, so this is like kind of a toy system where you can simulate like different level of like quantum dynamics. And here one example again. So here is based on so-called this quantum walk, and here also it is kind of high dimensional quantum walk. And as you see here, it's a 4-dimensional like picture, and the quantum walker evolves among different nodes of the here, and here particularly the approach we took is not only really like evolution of the particle through the network, but rather you mimic that evolution, mimic in a sense like you reproduce that evolution on a measurement. So measurement not on a computational basis, but on superposition basis. So in a sense, like you implement the unitary of the network on the unitary, using the unitary of the measurement. So this is the so-called measurement-based approach towards quantum computation, which was more for like in general used for continuous variable case, but here we used it for discrete variable, particularly for quantum walk. So with this, I conclude, and thank you all for your kind attention. And again, thank you for inviting me to give this talk. Okay.
Thanks, Syamsundar, for this nice overview. Now I invite questions. Already there are many asked, but you're welcome to ask.
So you mentioned that to perform these locality loophole tests, we have to preserve this entanglement over very large distances. How is it that over such large distances, this entanglement is preserved? Like, I assume you have to isolate it from the environment.
Yes. So for instance, photonics is ideal for, right? So because like photons is very prone to or let's say isolated from the environmental fluctuations, and also because of this telecommunication technologies, you can carry the photon over long distances with minimal amount of loss and so on. So that's why, because of all these tests could have done using, later on people have did it also with atoms and other systems, but initial atoms were using entangled photons.
How do we obtain like pairs of entangled particles for experiments?
From where is the question is coming? Yes, sorry. Yes, so as you saw, like in the first generation of experiment, it was from two-level transitions from an atom, but nowadays what people mostly use parametric down conversion. So it's a nonlinear process where you can think of you're one of the so-called pump photon, or one of the photon which is incident on the medium, decays to two photons, where you have this energy conservation as well as phase matching or momentum conservation. And so this nonlinear processes, it can be like a second order, third order, whatever.
Is there any feature of a quantum system which causes it to emit, let's say, a pair of entangled photons or entangled
Feature
electrons
of
a quantum system? Yes.
No, okay. So yes, of course, as I was saying, in quantum mechanical term, let's say the Hamiltonian of the process should give you something which you expect for an entangled state to be, and it turns out that, for instance, this parametric down conversion process, as I was saying, since it's maintaining, let's say, energy conservation, so you see, meaning given energy of this photon, or giving one photon in one beam, you are sure to get another photon in the other beam, because your energy conservation needs to be maintained. So this correlation. So starting from one photon, you create two photons. In the atomic case, again, you excite one level, and the two photon is emitted via another level in between. So the two photons emission should be correlated to the excitation photon.
Thank you.
Anyone else?
Yeah.
So maybe it's a little vague, the question. So, okay, so we now experimentally understand that the universe is quantum mechanical, like quantum mechanics works, but how do I reconcile, or do we know how to reconcile it with the idea of not having information flow faster than light, or should I not think of it that way?
And let me understand the question properly. So are you indicating that we are accepting quantum theory because we are accepting relativity, or is it along the same line? Or
yeah, so we accept that the universe behaves quantum mechanically. We've shown that experimentally.
Mm-hmm.
But without hidden variables, or if we don't want to invoke hidden variables, do we understand how it is consistent with relativity yet, or
no? I mean, not really. There is, to my opinion, there is. I do not know, to be honest. Is there a general theory combining both relativity and quantum mechanics?
So
I guess that's more business of string theory and so on. But anyhow, what this one is using, one of the outcome of the relativistic theory, that we cannot accept superluminal propagation of information. Okay? So given that at least this local hidden variable type of model should not be there. So it's not saying that there may not be another theory, but there is no existing theory as of now which can like supersede quantum theory.
Thanks.
I guess signals cannot propagate faster than light, even in that scenario. So even though there may be, yeah, you can't use it for any practical message passing. That's a constraint. Even though, yeah, useful information cannot be passed, even though there is, in some sense, superluminal transfer. Yeah, are there any other questions?
So in the initial experiment, the thought experiment that you showed, we had only one source, right? Or like one source was emitting two kind of the waves at two different wavelengths. Was it the case?
Yes, I mean here also in the practical experiments, if you maybe the figures was not very clear. So let's say in the first generation of experiments, if you look at the transitions, so for instance here, if you look at the transitions, there are two different wavelengths.
So
The two emitted
it's a
force.
single source.
Yes, I mean it's just two non-degenerate entangled photons. It can be perfectly acceptable. Its energy is conserved.
So I don't have a question, but I have a small correction in your initial slides. Just go in the initial.
Which one? This one?
Any second or third slides. Beginning.
Beginning.
Yeah.
Okay.
Second or third slide?
Yeah, here. Yeah. So here I think the next.
Which one?
Next slide.
Next one.
Next.
Yes, here. Here I think the orientation of the PBS is like not correct. It should be.
Yes. Perfect.
No.
Thank you very much. So that's a mistake people always say, okay, thank you for pointing this out. And people always say, if there is like wrong orientation of the polarizer, so you are not an experimentalist.
Yeah,
but unfortunately,
exactly.
still I did the mistake. So yeah, thank you. Thank you. But yeah, good job. I'm sure you are an experimentalist. Are you?
Yeah, he works with these.
Yeah, I did my case very badly. Too bad.
Okay, if are there any further questions? If there are none, thanks Syam for this very nice talk and
Thank you.
interesting
Thank you. It
discussion.
was really
Thank you very
wonderful.
much.
Thank you very much.
Before leaving, I would like to announce that let's invite Dr. Sangeeta Maini to thank Dr. Syamsundar Day for such a wonderful information.
So before I present the memento, I think it was a wonderful talk and we all benefited. And I think this was all arranged for us to get motivated, towards working in quantum technologies. And I would like to take this opportunity to remind you all that I have Quantum Technology Foundation is also dedicated to development of quantum technologies. So we all together can, take this mission forward. And I wish you all the very best of luck for that. So I thank Dr. Syamsundar for the wonderful presentation, and we look forward to working together in the future. Thank you so much.
Thank you very much. Thank you. Thank you. Thank you very much. Thank you.
Let's assemble here for a quick photo, a group photo. Please.